it will undergo what we call homolytic fission to give us the radicals. And now the radicals, they are the ones which will react with this methyl group, okay, to produce the substituted compound. But in presence of a halogen carrier, the halogen carrier induces this Br to form an electrophile that will receive electrons from the ring. Not so? Yes. And so our mechanism in this case is going to be, let's write the mechanism. It is going to be the Br, or our halogen. It is the same for all halogens. It will undergo what we call the homolytic fission, where this one will take up one electron, the arrow must touch. If your arrows are actually, I'm amazed, all of you, your arrows are touching. Okay? And we use half arrows to show that this reaction is reversible. The radicals formed here, they can still react with each other to produce a neutral molecule of bromine. So if you want, you can just put a 2 here, okay, and this becomes 2 bromide radical. Or if you want to be more fancy, you can just say the bromide radical and another bromide radical. So it depends on what's easy for you. Okay? Now these radicals formed, they are highly reactive compounds that they will react with this neutral molecule of methyl benzene. Not so? They will react with the neutral molecule of methyl benzene. Now they are not reacting with benzene, but rather the methyl group that is attached under benzene. Oh, this 3 is very far. So let's not write 3, let me write 2. Okay? Let me write 2. And then I spread the bond. So if you want, you can spread it this way. If you want, you can put H and then you spread. So whichever way you do, it will remain the same thing. And then the Br radical comes here, okay, where it will donate its 1 electron. If I find you using 2 arrows, anybody who uses 2 arrows, then that is wrong. Also, this one gets 1 electron, and then the remaining one is going to be taken up by the carbon. Not so? And so what shall we form? What shall we form? We shall form our phenyl methyl radical. Okay? This is our phenyl group, and the group is attached on the methyl radical. So that's why it is phenyl methyl radical. Oh, there is a 2. It's a 2. Let's erase this. So phenyl methyl radical, okay, and a neutral molecule of hydrogen bromide. So all of you had this step, which was brilliant. Okay, and then finally, not finally, because this is still chain propagation, our phenyl methyl radical is going to react with a neutral molecule. Not so? It is going to react with a neutral molecule. This is our phenyl methyl radical, which is 2 here, and then a dot. It's a dot. It's a dot. If you write this in an exam, I cross. It's a dot. Then reacts with a neutral molecule of bromine. It's a neutral molecule. If you put a radical like how some of you did, I cross. Okay? So whereby it's 1 electron that is moving, and 1 electron will come and pair up with 1 electron, okay, from the phenyl methyl radical, and then the remaining one is taken up by the Br. And so what shall we form? Then we shall form the phenyl bromomethane, sorry. Did you give the IUPAC name? What did you get? So this is our phenyl bromomethane okay, plus the bromide radical. As simple as this. Now the bromide radical here that is formed plus the bromide radical that remained, they will undergo what we call chain termination step, whereby the two radicals, the Br, okay, will react with another Br radical, okay, and since it's a mechanism, we have to show arrows. Somebody with a concern?
Open it up.
Pardon?
Sure, I'm lost there on the bromine molecule and radical. Because we had broken it up to radicals. Then why is it coming as a molecule again?
Oh, okay, that's a good question. That's good. Now, you are mixing, you see, this is a reaction vessel, okay? And in the reaction vessel, you put there your methyl benzene, okay? Your methyl benzene, and this is CH3, okay? And then you also put there bromine, maybe equal volumes. Now, you have very many bromine molecules, very many bromine molecules. Now, when you expose this to sunlight, it doesn't mean that all bromine molecules, all of them, they will dissociate to give you bromide radicals. No, some molecules will decompose, will undergo homolytic fission to give you the bromide radicals. Other molecules will remain in the reaction vessel as bromine molecules, as neutral molecules. Okay? So as a result, the radicals, they will initiate the reaction, but the propagation step, it continues whereby neutral molecules react with the radicals formed and neutral molecules react with the radicals formed until when all the, if it's in excess, for instance, all the CH3 is going to be replaced. But since this one is not in excess, then the bromine is the limiting reagent, whereby now at this step it is assumed that all the bromine molecules have reacted and there are radicals that are remaining within the reaction vessel. So therefore, to terminate the reaction, then the radicals cannot remain as radicals because they are unstable and highly reactive. So the radicals, they will react with the ferroradicals to produce bromine molecules. And the mechanism is as simple as that. Okay? So like I was saying, when we are marking, we shall put half a mark here and a full mark here, full mark and half a mark. Each step counts. So there is a video that is there. There is a video that we made about this very reaction in limited supply of bromine or halogen and in excess. Okay? And we used methane. So you can watch the video over and over and over again and practice so that it becomes part of you. Not so? Yes. Can we proceed now? Yeah, for the people who try to name this, let's name. Maybe let me use this pen. For the people who tried to name this, let me get some yellow. So people who tried to name this. Now, when the IUPAC name, you see, you have the functional group here. Okay? So this one is going to be taken as a parent chain. Okay? And therefore, this one is going to be taken as a functional group, and this one is going to be taken as a group that is attached on the parent chain. So that's how we shall name this. That's how we shall give the IUPAC name. The parent chain is this. Then the BR, like how you can see, it is a functional group, and then the benzene ring is going to be named as a group that is attached on the parent chain. And so the name is going to be, since it's 1, then there is no need of writing 1. Okay? Otherwise it would have been 1 phenyl. But there is no need of writing 1. So it will just be phenyl, okay? And then bromo, because the halogens are named. It's a halogen first, and then the parent chain. And this one, since it's just 1 carbon atom, then it will be bromomethane. Okay? Bromomethane. So it is as simple as that. Phenyl bromomethane. So for us who named, you named bromo, methyl bromobenzene. Now that is something different. If you named methyl, some of us named methyl, then bromobenzene. This is what you named. Now because there is no data, it means the methyl is on carbon 1 and the bromide is also on carbon 1, but all of them are attached on benzene. So if I'm to sketch it here, let me get some different pen. The words are becoming many. So if I'm to sketch it, I'll write my benzene ring. If I'm to sketch what you have named for us, I write my benzene ring, okay? And that's a benzene ring. And then the methyl group is on carbon number 1 since there is no data behind. So any can be carbon number 1. So you have a methyl group, okay? And the the bromide is also on carbon number 1 because there is no data behind. So the bromide is also on carbon number 1. So this is the bromide. And then bromobenzene. So this is what you have named. And what you have named is totally different from what you have. So I hope it is really good. In case there are queries, it's okay. If the question is immediate, if the question requires immediate attention, you can unmute and ask. You know how we've been doing it. If it doesn't require immediate attention, then you can use the chat box. So let's proceed and talk about chlorobenzene. And with this, the chloride atom substitutes one of the hydrogens on the benzene ring. And it is also an ortho-para director. However, this one does not activate the ring. So for instance, if this is my benzene, this is my benzene, and the ring is like this. So the chloride is on carbon number 1. And like I told you, this is a disclaimer, or this is a reminder. Oh, I'm writing up. Sorry for that. Instead of writing a chloride, I'm writing a methyl. So is it because we are from studying a methyl group? So this is a Cl, okay, that is attached. Now, it's not that this is carbon number 1. It's another disclaimer, or it's another, let me assert this. If you just draw benzene like this, okay, any carbon atom can be carbon number 1. Any carbon atom. This can be carbon number 1, this can be carbon number 1, this can be carbon number 1. Same. But once a group attaches, whether it attaches here, okay, and this is Cl, then this carbon that has a group becomes carbon number 1. Okay, so that if I bring and attach maybe another group here, maybe a Br, now this one is preferred to this. Okay, so therefore this is going to be carbon 1 and this one is going to be carbon 2. Maybe if I attach another group, maybe the OH, Now the OH is preferred to this and this. So therefore this becomes carbon 1, and then you add the value that gives you the lowest locant. It's the side that you take, or the side that it's the side that you take. We shall study these polysubstituted compounds, yeah, where the benzene has more than one groups. We shall study them once. So therefore with chlorine or with chlorobenzene, the halogen or the chloride in this case attaches on a benzene ring. Now it deactivates the ring, however, the incoming electrophile is directed to the ortho para position. Now why does it deactivate the ring? It's because it is more electronegative than the carbon atom here. So it tries to withdraw the bonding electrons from the carbon more to itself. Okay? And so if you withdraw the bonding electrons from this carbon, the same effect will be attributed to these pi electrons, these pi delocalized electrons in a ring, so that they are not available to the incoming electrophile. Okay? But however, when it is forced to react, then the incoming electrophile is going to attach on the ortho and para positions of the ring. Not so? Yes. So the halogens have got a negative inductive effect, that is they are more electronegative, and so they withdraw the electrons from the ring towards themselves, so that the pi electrons on the ring cannot easily be availed, so that's why they make the reaction much slower. But once you pull them, then the electrons, the pi electrons, they will be availed on the position 2 and 4, okay, where you have the high electron densities, so that the incoming electron attaches where? On the ortho, which is carbon 2, and the para position, which is carbon number 4. Okay? So for instance, you can do nitration. Okay? You can do nitration and see the mechanism is the same, everything is the same, conditions are the same. With the other methyl, how we can add a methyl group, you can. However, you do this in the free time. Okay? You can even do for all. Do nitration, do halogenation, how you can add a halogen group, do alkylation. Okay? Do alkylation. You can repeat everything like how we've been doing it. Which other one? Sulfonation. All the reactions of benzene. And all the reactions, all this, they will attach on the ring. And where are they going to attach? Okay? They are going to attach on the ortho and the para position. So, in your free time, please do this. Okay? Please do. And you can send me your answers via WhatsApp. And I have a look at your mechanisms. Okay? So that I can comment or comment accordingly. Not so? Yes. Let's proceed to benzoic acid. Yes. Now with benzoic acid, this is a ring where the one of the hydrogens is substituted by a carboxyl group. Okay? One of the hydrogens is substituted with a carboxyl group. And this is a carboxyl group, COOH. So it substitutes the hydrogen. Not so? Yes. It substitutes the hydrogen. And this group has a big impact on the reactivity of this ring. The impact is so much. Okay? As we are going to see. Whereby, let's have a look. If this is the ring, let me draw something big. If this is the ring, and you have the carbon atom, and the carbon is bonded to oxygen, and then there is another OH. Can you imagine? So such a compound whereby the carbon is less electronegative, the oxygen is more electronegative. Oh, you have. So the oxygen is more electronegative than the carbon. The same applies to this. So this oxygen will pull the electrons, and also this one will also pull the electrons, so that the effect is distributed to this carbon atom, which will also distribute the same effect to this carbon atom. Hence you end up withdrawing these pi electrons, hence making them unavailable for the incoming electrophile. So that's why, if you remember in the other previous lesson, we were arranging these elements in order of decreasing and increasing reactivity towards electrophilic substitution reaction. You remember what we did, how the orders that were. So that is the same concept. Not so? And so how are we going to produce now? Formation of benzoic acid is key, especially in organic synthesis. Formation is key, especially in organic synthesis. And with the benzoic acid, for instance, is formed by oxidation of methyl benzene. Okay? So if we have our methyl benzene, for instance, this is our methyl benzene. Okay? Methyl benzene, and there is a methyl group here. If I oxidize it, then I'll form benzoic acid. Now in your mind, you should be thinking of the conditions here. Okay? In your mind, you should be thinking of the conditions. Not so? And the conditions are simple. We have looked at all of them in the process as we've been studying. We saw all of them. We did reactions. We did synthesis. You know. So now in this case, we want to produce methyl benzene. Then we shall use a strong oxidizing agent. And there are usually two. The first one, we can use acidified potassium manganate 7, or you can say acidified potassium permanganate. This reaction is key in presence of an acid. For instance, now here we shall use sulfuric acid, dilute sulfuric acid. You can't use dilute nitric acid, neither can you use dilute HCl. Why? They react with this instead of acidifying. So if you want, you can just say hydrogen ions. It is still the same thing. Okay? So it is acidified potassium manganate 7. And then we need to do the warming. We shall do some warming. Okay? So if you hit this, then the methyl group that is here, it will be oxidized to a carboxyl group. This reaction is key. That's one. Number two, you can use, instead of, if you don't have maybe the potassium permanganate, then you can use potassium dichromate 6. Okay? Potassium dichromate 6. Still acidified. And you still use dilute sulfuric acid. Okay? No other acid. If you use HCl, then it will react with this. If you use nitric acid, still it will react with this. And the reaction won't occur. So here we shall use sulfuric acid. And then we do the heating. So these two, they are the common oxidizing agents that we have in a laboratory. So if you react these two, this one with a methyl group here, it will be oxidized to this. Similarly, when you react potassium permanganate, with sulfuric acid and heat, then we shall form the benzoic acid. For instance, you try out this. try out this. You try out this. And we have talked about almost everything. Before that. So you try out this. I want you to synthesize. You effect this reaction. Show how you can prepare this from a lab. Show how you can prepare, okay, how you can effect this reaction in a laboratory. I want you to prepare from benzene, okay. Let me even complicate things a bit. You have phenol in a laboratory, but you want to prepare benzoic acid. What are you going to do? Which reactions are you going to do to produce the phenol? So you do this. I have a look at it. And the other time I gave you this and somebody wrote a mechanism. Here it is synthesize benzoic acid from phenol. Show how you can prepare benzoic acid from phenol. So can you please do that? Chap chap. Guys, do that chap 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 chap. Yes, I've seen your work and you tried, however, those minor mistakes, they are enough to deny you marks. So the first thing that we do here, we shall form our benzene. We shall form our benzene, okay, and then from benzene we shall produce our benzoic acid, okay. We shall produce our benzoic acid, shall produce our methyl benzene, and then from methyl benzene we produce benzoic acid. So here we saw the reaction, okay, and the reaction was zinc. Here we use zinc dust. Zinc, it's a powder, and then we do the heating, okay. We shall take away the OH and we produce our benzene, not so. And then sorry for this, we have a methyl group, and then here we shall add a methyl group. How? Use any halogen, maybe bromomethane or chloroethane, any, okay. So let's use Cl in presence of any halogen carrier. Maybe we can use iron 3, or somebody can use aluminium 3, okay, aluminium 3 chloride, or somebody can use boron 3 chloride, any halogen carrier that you think you want to use, you can use it. So we shall add this methyl group, and then after we shall oxidize, okay, using a strong oxidizing agent, not so. And in this case it is potassium manganate 7 or potassium permanganate, and it must be acidified and heated. So basically it's as simple as this. So when you're watching the video, it's better when we reach where I give work, it's better you pause that video, and then after pausing that video, then you do, after doing, then you proceed with the video, okay, so that you practice enough. So that's benzoic acid and how important this reaction is. Now like I've told you, the benzoic acid, that carboxyl group that is attached on the ring with the 3 oxygen atoms, with 2 oxygen atoms that are highly electronegative. The oxygen atoms strongly attract the bonding electrons from carbon, okay, so that the carbon also attracts the delocalized electrons, which makes it unavailable for bonding for the incoming electrophile. So it strongly deactivates the ring, and therefore the incoming electrophile can only and only attach on the carbon number 3 that has electrons. Not so? That has a relatively higher electron density. And in the other lesson, I showed you how, okay, the carbon 3 on the meta position has a high electron density for these groups that do deactivate the ring. So when I give you a reaction, maybe for instance I give you benzoic acid, let's use red pen. For instance, I give you benzoic acid, okay? I give you benzoic acid, I give you benzoic acid, COOH, and I say alkylation of benzoic. The reactions are the same, however, this one is slow compared to, so I react it with CH3, okay, and then Br in presence of maybe aluminium bromide, which is a halogen carrier, okay. Then the compound formed, okay, if this is your benzene and this is your COOH, now somebody is going to complain that, sir, the carboxyl group is on this, is on carbon, and now you put it here. I've told you it's the same. Whether you put it here, that position where the group is becomes carbon 1. So even if I do this, it is still carbon 1. Nothing has changed. Okay? So therefore, this group, it is a meta director. Okay? It directs the incoming electron to the meta position, to carbon number 3. So the group must be here. CH3, CH3. So if I have, if you write for me such a product, then I will just cross you, with no mercy. So this is my benzoic, my carboxyl group, and you write for me this. I will just cross you with no mercy. Or you don't put it here and you put it here. I will just cross you with no mercy. Okay? Because this shows that you are not a chemistry student. You never attended any chemistry lessons. Okay? You never attended any chemistry lessons. But if you attended some chemistry lessons, such as this, then you know that this group, it deactivates the ring, so it is a meta direct. The incoming electrophile must therefore attach on carbon number 3. Not so? Yes, that's brilliant. That's good work. Any queries? You are free to ask. Then, this is our last slide, and then we call it a day. For reactions where on a ring you have more than one groups, 2 or more groups, okay, then obviously one group is going to be given that it is going to be preferred than the other, but the incoming electrophile attaches on the overall effect, on the resultant effect of these groups on the ring. What am I talking about? Let's see. Let's say we have such, you have such a compound, okay, and you have the OH here, okay, you have the OH here, and you have the NH here. So these are more than one groups. Now and the question says, where is the incoming electrophile going to attach to? Now the answer is simple. You can see with this, the OH, it is an ortho, okay, and para position. So this is ortho and para position. So it directs the incoming electrophile to the ortho position and to the para position, this OH. But the nitro group also, for it, it's a meta director, whereby, and a meta director, according to this nitrogen, it is this and this. Okay? So the incoming electrophile, when it's coming, okay, when it is going to attach on this benzene, it will either attach here or here. Okay? Now for me, I call it madness. When I give you such, maybe I've given you this and I want you to add a methyl group, okay, CH3 and then Cl, and then in presence of aluminium chloride, for instance, and I find your CH3 here, or I find your CH3 here. Now this shows that you never attended any chemistry lessons. So it either goes here or it goes here. But now still, if it goes here, it will receive some repulsion with this OH. So it's better it attaches itself here, where it has no other groups to repel it. So therefore, the major product that will be formed in such a compound is going to be, so this is your ring, okay, and you have the OH here, and you have the nitro group here, okay, and this will be the major product. You have the CH3 here. So as simple as that, this is the major product, and the minor product is going to be the one with the CH3 here. This one, let me write it. You know, if I don't write it, you'll be like, hey teacher, what's that? So you have, this is a ring, and you have the OH, okay, and you have the nitro group here, okay. So the minor product is going to be this, whereby there is no way how you can form the CH3 here, neither can you form the CH3 here. Why? Because these carbon atoms are electrophilic, they don't have the electrons. It is this carbon atom and this carbon atom that are electron rich. So therefore, the incoming electron attaches where? On this or this. But for this, you can see it is neighboring this OH. So the two can repel each other. So to avoid that inductive effect and repulsive, which makes the overall molecule unstable, then it will attach on this. Okay? And so you form this as your major product. So basically, it is as simple as that. So it is as simple as that. Now, how about when you are naming, okay? And you are naming a compound that has more than one group, then this order is considered. Whereby, where the O is attached on the ring, it is given the first priority. Then followed by where the nitrogen is attached, followed by the alkyl group, and then halogen and meta directors. Even the order of reactivity, actually this is the order of reactivity. Okay? Yes, not nomenclature. So the order of reaction is going to be this. Why oxygen? Because oxygen, it donates electrons, okay, towards the ring compared to the nitrogen. So the order is going to be, for that where the oxygen is attached, okay, then followed by where the nitrogen is attached, then alkyl group, halogen, and finally meta directors. Okay? Yes. So whereby if the in case like how, okay, let me give you this example and then we call it a day. That's too much. For instance, you might have this. This is also too much. You might have this. Okay? You might have this. And you have O here. And it is OCH3. Okay? And you have the CH3 here. Okay? And maybe you have the halogen here. The CH, the Cl here. Now for such a compound, the question wants where is the incoming electrophile going to attach? Okay? The incoming electrophile, where is it going to attach on such a compound? So, like always, the where the O is attached, it is given that first choice. So it will attach on the ortho and para position. Okay? Then followed by this. So the methyl group, it directs on the ortho. So the ortho here has to, and then this ortho, and then the para position. So this is the para position. Okay? Then for the Cl, it directs on the ortho, and this is the ortho. It's ortho, that's what I mean. And then the para position. So now you can see that this carbon atom is favored. Eh? It has three groups that are directing the incoming electrons towards it. But this one you just have two, this one just have two. So therefore the incoming electrophile attaches on the ortho position to in response or in relation to this group. So it is basically as simple as that. So I think that's how we finish benzene, reactions of benzene and derivatives of benzene. Now, in another topic, we shall talk about halogen alkanes or alkyl halides. Halogeno alkanes. So you can do some reading. Halogeno alkanes, or you can call them alkyl halides. And whenever I'm teaching organic chemistry, alkyl halides, and I finish benzene, then I consider myself done with organic chemistry. Why? Because the rest is just repeating, okay, what we have been talking about. There is nothing new. Don't mind about that one. He's watching soccer. So there is nothing new. Okay? Everything is just repeating what we have been talking about. So I think we can call it a day.